Hello there, and welcome to the Sleepy Library. Tonight, we are drifting into the mysterious realm of quantum physics, where reality itself becomes fluid and particles dance between existence and possibility. This is a journey into the smallest scales of nature, where the rules we know begin to bend and shimmer like light through water. Quantum physics is not just equations on a blackboard. It is the hidden language of atoms, electrons, and photons. It is the silent architecture beneath everything you see and touch. And though it defies our everyday intuition, it is beautifully, quietly real. If you enjoy these gentle explorations into the mysteries of science, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, just breathe. Let the night settle around you and allow your mind to soften. Let's begin. Quantum physics describes the world at the smallest scales. Long before atoms were photographed, before electrons were seen, scientists suspected that matter was not infinitely divisible. They believed there must be a bottom layer, a foundation of tiny pieces that could not be broken down any further. This intuition was correct. At scales smaller than you can imagine, smaller than the tip of a needle, smaller even than a virus or a single cell, lies the quantum realm. Here, particles like electrons, photons, and quarks follow rules that seem impossible by our everyday standards. Yet these rules are not fantasies. They are real, tested, and confirmed in laboratories around the world. Quantum physics is the study of this realm, the science of the very small. It governs how atoms hold together, how light behaves, and how energy moves through space. Without quantum physics, we would not understand chemistry, biology, or the structure of matter itself. It is the foundation beneath the visible world, humming quietly in every atom of your body. The word quantum means how much. The term quantum comes from Latin, meaning a specific quantity or amount. In physics, it refers to the discovery that energy and matter are not smooth and continuous, but come in discrete packets called quanta. This was a radical idea when it first emerged in the late 1800s. Before quantum theory, scientists thought energy flowed in smooth waves, like water poured from a pitcher. But experiments began to show something strange. Light, for instance, did not behave like a continuous wave in all situations. Sometimes it acted as though it were made of tiny particles, each carrying a fixed amount of energy. These particles came to be called photons. The idea of quanta meant that nature has limits, boundaries, and smallest possible units. You cannot have half a photon. You cannot divide energy infinitely. At the smallest scales, nature is grainy, not smooth. This discovery changed everything, opening the door to a new way of understanding reality. Quantum physics arose from puzzles that classical physics could not solve. In the early 1900s, physicists encountered several mysteries that defied explanation. One was called blackbody radiation, the way objects glow when heated. Classical theories predicted that hot objects should emit infinite amounts of ultraviolet light, which was clearly not happening. Another puzzle involved the photoelectric effect, where light shining on metal could knock electrons loose. But the energy of the ejected electrons did not depend on the brightness of the light, only on its color or frequency. This made no sense under the old rules. Max Planck solved the blackbody problem by proposing that energy is released in discrete chunks, not continuously. Albert Einstein extended this idea to explain the photoelectric effect, suggesting that light itself is quantized into photons. These breakthroughs laid the foundation for quantum mechanics. They showed that the universe, at its core, operates in ways that defy our intuition but follow precise mathematical laws. Particles behave like waves, and waves behave like particles. One of the most beautiful and perplexing discoveries of quantum physics is wave-particle duality. Light can act like a wave, spreading out and interfering with itself to create patterns. But it can also act like a particle, arriving in discrete packets of energy. Electrons, which we think of as tiny particles, can also behave like waves, forming interference patterns just like ripples on water. This dual nature is not a contradiction. It is simply how quantum objects are. They are neither purely wave nor purely particle. They are something else, something that contains both possibilities. Which behavior you observe depends on how you look. If you design an experiment to detect particles, you will see particles. If you design it to detect waves, you will see waves. The object itself does not change. What changes is how it reveals itself to us. This duality lies at the heart of quantum mechanics, reminding us that reality at small scales is richer and stranger than we once imagined. Quantum mechanics deals with probabilities, not certainties. In the everyday world, we are used to certainty. If you drop a ball, it falls. If you push a box, it moves. But in the quantum world, certainty dissolves into probability. Quantum mechanics does not tell you exactly where an electron is. It tells you where it is likely to be. It does not predict the precise outcome of a measurement. It predicts the odds of different outcomes. This probabilistic nature troubled many early physicists, including Albert Einstein, who famously said he did not believe that the universe plays dice. But experiment after experiment has confirmed that quantum mechanics is correct. The world, at its smallest scales, is inherently uncertain. This does not mean quantum physics is vague or unreliable. On the contrary, its predictions are astonishingly accurate. It simply means that nature, at the quantum level, leaves room for chance. Particles exist in clouds of possibility until they are observed. Then, suddenly, one possibility becomes real. This is not a flaw in the theory. It is a feature of reality itself. The Heisenberg uncertainty principle sets fundamental limits on knowledge. Werner Heisenberg discovered one of the most profound truths about the quantum world. There are certain pairs of properties that cannot both be known precisely at the same time. The most famous example is position and momentum. The more precisely you know where a particle is, the less precisely you can know how fast it is moving, and vice versa. This is not a limitation of our measuring tools. It is a fundamental feature of nature. Uncertainty is built into the fabric of reality. At the quantum level, particles do not have exact positions and exact speeds simultaneously. They exist in a kind of haze, a spread of possibilities. When you measure one property sharply, the other becomes blurred. This principle has profound implications. It means that at the smallest scales, the universe is not deterministic. You cannot, even in principle, predict the future with perfect accuracy. There is always a limit, a boundary beyond which knowledge cannot reach. Yet this uncertainty is not chaos. It follows strict mathematical rules, and those rules describe the world with extraordinary precision. Quantum superposition allows particles to exist in multiple states at once. In classical physics, an object is in one state at a time. A coin is either heads or tails. A light switch is either on or off. But in quantum mechanics, objects can exist in a superposition of states, experiencing multiple possibilities simultaneously. An electron, for example, can be in a superposition of being in two places at once, or spinning in two directions at once. This is not a metaphor. It is a literal description of how quantum systems behave before they are observed. Superposition is the reason quantum particles can interfere with themselves, creating the wave-like patterns we see in experiments. When a particle is in superposition, it follows all possible paths through space, and those paths overlap and interact. Only when a measurement is made does the superposition collapse, and the particle settles into one definite state. This collapse is one of the deepest mysteries in physics. We know it happens. We can predict when it happens, but we do not fully understand why. Quantum entanglement links particles across vast distances. Perhaps the strangest phenomenon in quantum physics is entanglement. When two particles become entangled, their properties become correlated in a way that seems to defy the limits of space and time. If you measure one particle and find it spinning in a certain direction, you instantly know the spin of the other particle, no matter how far apart they are. This connection is not due to any signal passing between them. It is not limited by the speed of light. It is something deeper, a kind of shared existence that Einstein called spooky action at a distance. He was deeply troubled by this, believing it suggested that quantum mechanics was incomplete. But decades of experiments have confirmed that entanglement is real. Particles separated by kilometers, even by continents, can remain entangled. Measuring one affects the state of the other instantaneously. This does not allow faster than light communication, so it does not violate relativity, but it does mean that the universe is fundamentally non-local. Particles that were once together remain connected in a way that transcends ordinary space. Bell's theorem proved that the quantum world is truly non-local. In 1964, physicist John Stuart Bell devised a way to test whether quantum entanglement could be explained by hidden variables, some underlying reality that we simply had not discovered yet. He derived an inequality, a mathematical limit that any theory based on local realism must obey. Local realism is the idea that objects have definite properties independent of observation, and that influences cannot travel faster than light. Bell showed that if local realism is true, certain measurements on entangled particles must produce correlations below a specific threshold. But quantum mechanics predicts correlations that violate this threshold. Experiments, starting in the 1970s and continuing to the present day, have consistently confirmed that quantum mechanics is correct. The correlations are stronger than any local theory allows. This means that the universe does not obey local realism. Either particles do not have definite properties until measured, or influences can propagate faster than light, or both. Bell's theorem is one of the most profound results in all of science. It tells us that reality is far stranger than we imagined. Quantum mechanics is the most accurately tested theory in science. Despite its strangeness, quantum mechanics is not speculation. It is the most precisely verified framework in all of physics. Predictions made by quantum electrodynamics, the quantum theory of light and matter, have been confirmed to better than 1 part in 10 billion. The magnetic properties of the electron, for example, match theoretical predictions to an astonishing degree of accuracy. Every technological device that relies on semiconductors, lasers, or transistors is a testament to the correctness of quantum mechanics. Your smartphone, your computer, even the LEDs that light your home all function because engineers understand quantum physics. The theory has been tested in countless experiments over nearly a century, and it has passed every test. If quantum mechanics were wrong, the modern world would not work. Its success is not just academic. It is practical, tangible, and undeniable. The double-slit experiment reveals the mystery of quantum behavior. One of the most iconic experiments in physics is the double-slit experiment. Imagine shining light through two narrow slits cut in a barrier. On the other side, the light creates an interference pattern, a series of bright and dark bands. This pattern shows that light behaves like a wave, with peaks and troughs overlapping and cancelling each other out. But when you send light through one photon at a time, something remarkable happens. Each photon arrives as a single point, like a particle. Yet over time, those points build up into the same interference pattern. Each photon seems to interfere with itself, as though it passes through both slits at once. The same behavior occurs with electrons, atoms, and even molecules. When you try to observe which slit a particle goes through, the interference pattern disappears. The act of observation changes the outcome. This experiment captures the essence of quantum mechanics in a single setup. It shows that quantum objects are neither purely wave nor purely particle. They are both, and the universe decides which aspect to reveal based on how we look. Quantum tunneling allows particles to pass through barriers they should not be able to cross. In classical physics, if a ball does not have enough energy to roll over a hill, it stops and rolls back. But in quantum physics, particles can tunnel through barriers even when they lack the energy to go over them. This phenomenon, called quantum tunneling, arises from the wave nature of particles. A particle's wave function extends slightly beyond a barrier, creating a small probability that the particle will appear on the other side. This probability is usually tiny, but it is not zero. Quantum tunneling is not just a curiosity. It is essential to the universe as we know it. The sun shines because of quantum tunneling. Inside the sun's core, hydrogen nuclei fuse to form helium, releasing energy. But the nuclei are positively charged and repel each other. Without tunneling, they could never get close enough to fuse. The temperatures and pressures in the sun's core are not sufficient on their own. Tunneling makes fusion possible, allowing stars to burn for billions of years. On Earth, tunneling is used in technologies like scanning tunneling microscopes, which can image surfaces at the atomic level, and in electronic devices like tunnel diodes. Quantum mechanics governs the structure of atoms. Atoms are the building blocks of matter, and their structure is entirely quantum mechanical. In the early 1900s, scientists knew atoms contained electrons and a nucleus, but they did not understand why electrons did not simply spiral into the nucleus, collapsing the atom. Classical physics could not explain it. Quantum mechanics provided the answer. Electrons in an atom do not orbit like planets around the sun. Instead, they exist in regions called orbitals, which are probability clouds describing where the electron is likely to be found. These orbitals have specific, quantized energy levels. An electron cannot exist between these levels. It can only jump from one level to another by absorbing or emitting a photon. This quantization explains why atoms emit and absorb light at specific wavelengths, creating the spectral lines that allow us to identify elements. It also explains the structure of the periodic table. The arrangement of electrons in their quantized energy levels determines an element's chemical properties. Quantum mechanics is the reason chemistry works. Photons are particles of light with zero mass. Light is made of photons, tiny packets of electromagnetic energy. Photons are strange objects. They have no mass, yet they carry momentum. They travel at the speed of light, and from their perspective, time does not pass. They are born when electrons jump between energy levels, and they vanish when they are absorbed. Each photon carries a specific amount of energy determined by the frequency of the light. Higher frequency light, like blue or ultraviolet, has more energetic photons. Lower frequency light, like red or infrared, has less energetic photons. This is why ultraviolet light can damage your skin, while red light cannot. Photons do not experience time or distance. From a photon's point of view, it is emitted and absorbed in the same instant, even if it travels across the universe. This timeless existence is one of the many strange consequences of relativity and quantum mechanics combining. Photons are the messengers of the electromagnetic force, carrying energy and information across the cosmos. Electrons are identical and indistinguishable from one another. Every electron in the universe is exactly the same. There is no way to tell one electron from another. They have the same mass, the same charge, and the same spin. This indistinguishability is not just a practical limitation. It is a fundamental property that has deep consequences. When you swap two electrons, nothing about the system changes. The universe does not keep track of which electron is which. This leads to strange statistical behaviors that differ from classical physics. Electrons obey Fermi-Dirac statistics, which means they cannot occupy the same quantum state simultaneously. This is called the Pauli exclusion principle, and it is the reason atoms have structure. Without it, all electrons would fall into the lowest energy state, and matter as we know it would not exist. Indistinguishability also plays a role in quantum computing. Qubits, made of indistinguishable particles, can be manipulated in ways that classical bits cannot, enabling new forms of computation. The Pauli exclusion principle explains why matter is stable. Wolfgang Pauli discovered that no two electrons in an atom can have the same set of quantum numbers. In other words, they cannot occupy the same state at the same time. This exclusion principle is what gives atoms their size and structure. If electrons could all collapse into the lowest energy level, atoms would be far smaller and denser. Matter would behave completely differently. The exclusion principle also explains the structure of the periodic table. Electrons fill up energy levels one by one, starting from the lowest. Each level can hold a limited number of electrons. When a level is full, the next electron must go into a higher level. This filling pattern determines an element's chemical behavior. The exclusion principle is also responsible for the stability of white dwarf stars and neutron stars. When a star runs out of fuel, gravity tries to collapse it. But the exclusion principle resists this collapse, creating a pressure that can hold the star up against gravity, at least for a while. Quantum mechanics explains how lasers work. A laser is a device that produces a beam of light that is coherent, meaning all the photons are in phase, traveling together like a marching band. This is very different from ordinary light, where photons are emitted randomly and travel in all directions. Lasers work through a process called stimulated emission, a purely quantum phenomenon. When an atom is in an excited state, it can emit a photon and drop to a lower energy state. Normally this happens randomly, but if a photon with just the right energy passes by, it can trigger the atom to emit another photon that is identical to the first. This second photon has the same frequency, phase, and direction. By placing atoms in a cavity with mirrors, photons bounce back and forth, stimulating more and more emissions until a powerful beam of coherent light builds up. Lasers are used in countless applications, from reading barcodes and playing music on CDs to performing surgery and cutting metal. They are a direct technological application of quantum mechanics, demonstrating how understanding the quantum world leads to powerful tools. Quantum mechanics is essential for semiconductors and transistors. The modern world runs on semiconductors. Every computer, smartphone, and electronic device relies on transistors, tiny switches made from semiconductor materials like silicon. These transistors are quantum devices. Their operation depends on the quantum properties of electrons moving through materials. In a semiconductor, electrons can exist in two regions, the valence band and the conduction band. The energy gap between them determines whether the material conducts electricity. By doping the material with impurities, engineers can control this gap and create regions where electrons flow easily or not at all. Transistors use this control to switch currents on and off, forming the binary logic that underlies all computing. As transistors have shrunk to nanometer scales, quantum effects like tunneling have become both challenges and opportunities. Engineers now design with quantum mechanics in mind, creating devices that exploit quantum behavior rather than fight it. Without quantum physics, the information age would not exist. Quantum field theory describes particles as excitations of fields. Quantum mechanics, as originally formulated, describes particles like electrons and photons. But a deeper framework, called quantum field theory, shows that particles are not fundamental objects. Instead, the universe is filled with fields, one for each type of particle. An electron is an excitation, a ripple, in the electron field. A photon is an excitation in the electromagnetic field. This perspective resolves many puzzles. It explains how particles can be created and destroyed, how they interact, and why certain symmetries hold. Quantum field theory is the foundation of the standard model of particle physics, the most complete description we have of the fundamental forces in particles. It describes electromagnetism, the weak nuclear force, and the strong nuclear force, with extraordinary precision. It predicted the existence of particles like the W and Z bosons and the Higgs boson, which were later discovered in experiments. Quantum field theory is mathematically complex, but its predictions are stunning. It accounts for phenomena from the behavior of quarks inside protons to the scattering of light by electrons. The Higgs boson gives particles their mass. One of the greatest mysteries in physics was why particles have mass. According to the standard model, particles like electrons and quarks should be massless, traveling at the speed of light, but clearly they are not. In the 1960s, physicists proposed a solution. There is a field called the Higgs field, that permeates all of space. Particles interact with this field, and this interaction gives them mass. The stronger the interaction, the more mass the particle has. Photons do not interact with the Higgs field, so they remain massless. The Higgs field also implies the existence of a particle, the Higgs boson, which is an excitation of the field. For decades, physicists searched for this particle. In 2012, experiments at the Large Hadron Collider confirmed its existence. The Higgs boson has a mass of about 125 times that of a proton, and its discovery was a triumph of theoretical and experimental physics. It completed the Standard Model and confirmed that our understanding of how particles acquire mass is correct. Quantum mechanics is probabilistic, but not random. There is a difference between probability and randomness. Quantum mechanics is probabilistic, meaning it predicts the likelihood of outcomes, but it is not random. The evolution of a quantum system follows precise mathematical rules given by the Schrödinger equation. If you know the initial state of a system, you can predict how it will evolve over time. What you cannot predict is the exact outcome of a measurement. You can only calculate the probabilities of different results. This distinction is important. The probabilistic nature of quantum mechanics is not due to ignorance or incomplete information. It is a fundamental property of nature. Particles genuinely exist in superpositions of states, and measurement causes a real, physical change. This is very different from classical probability, where uncertainty arises from not knowing all the details. In quantum mechanics, even if you know everything the theory allows, some outcomes remain uncertain. This is not a defect. It is how the universe works. The Schrödinger equation governs the evolution of quantum systems. Erwin Schrödinger formulated an equation that describes how quantum systems change over time. It is the quantum analog of Newton's laws of motion. The Schrödinger equation takes a wave function, which encodes the probabilities of a particle's position and momentum, and shows how it evolves. Solving the Schrödinger equation for different systems reveals the behavior of atoms, molecules, and particles. For a hydrogen atom, the solutions give the energy levels and orbitals of the electron. For a particle in a box, they show how the particle's wave function is confined. The equation is deterministic in the sense that it evolves the wave function smoothly and predictably. But when a measurement is made, the wave function collapses in a way that the equation does not describe. This collapse is one of the unresolved questions in quantum mechanics. Despite this gap, the Schrödinger equation has been extraordinarily successful. It is the foundation of quantum chemistry, solid-state physics, and much of modern technology. Quantum superposition is destroyed by decoherence. If quantum objects can exist in superpositions of states, why do we not see superpositions in everyday life? Why is a chair not in two places at once? The answer lies in a process called decoherence. When a quantum system interacts with its environment, which includes air molecules, photons, and other particles, the delicate superposition becomes entangled with the environment. Information about the superposition leaks out, and the system loses its quantum coherence. It behaves as though it has collapsed into a definite state. Decoherence happens very quickly for macroscopic objects. The larger and warmer an object, the faster it decoheres. This is why we do not observe quantum effects in everyday life. By the time we can look at something, it has already decohered into a classical state. But in carefully controlled conditions, scientists can isolate systems and maintain superpositions for long enough to observe quantum effects. Decoherence is one of the main challenges in building quantum computers, which rely on maintaining superpositions of qubits. Quantum mechanics underlies the stability of matter. Why does matter not collapse in on itself? Quantum mechanics provides the answer. The uncertainty principle prevents electrons from falling into the nucleus. If an electron were confined to a very small region near the nucleus, its momentum would become highly uncertain, giving it a large kinetic energy. This energy is high enough to keep the electron in a larger orbital, balancing the attraction to the every nucleus. The result is a stable atom. Similarly, quantum mechanics explains why solids are rigid. Electrons in a solid obey the Pauli exclusion principle, which prevents them from occupying the same state. This creates an effective repulsion that resists compression. When you press on a table, you are feeling the quantum mechanical forces between electrons. Without quantum mechanics, matter would not have the properties we observe. Atoms would collapse, and the universe would be unrecognizable. Quantum effects play a role in photosynthesis. Photosynthesis is the process by which plants convert sunlight into chemical energy. For a long time, it was thought to be a purely classical process, governed by the laws of chemistry and thermodynamics. But recent discoveries suggest that quantum mechanics plays a crucial role. Inside the molecular machinery of photosynthesis, energy absorbed from light must travel from where it is captured to where it is used. This journey happens with remarkable efficiency, far higher than classical processes would allow. Experiments indicate that the energy exists in a quantum superposition, exploring multiple pathways simultaneously. This allows the system to find the most efficient route almost instantaneously. Quantum coherence, the same property exploited in quantum computers, appears to be at work in the nanoscale structures of plant cells. This discovery is surprising and profound. It suggests that life itself may use quantum effects to function optimally. The boundary between quantum and classical is not as sharp as once thought. Even in warm, wet, noisy biological environments, quantum mechanics can play a role. Quantum mechanics allows for the existence of antimatter. For every type of particle, there is an antiparticle with the same mass but opposite charge. Electrons have anti-electrons, also called positrons. Protons have antiprotons. When a particle meets its antiparticle, they annihilate, converting their mass into energy according to Einstein's equation E equals mc squared. Antimatter is not science fiction. It is real and has been created in laboratories. Positrons are used in medical imaging techniques like PET scans, where they annihilate with electrons in the body, producing gamma rays that reveal internal structures. The existence of antimatter was predicted by Paul Dirac when he formulated a version of the Schrödinger equation compatible with relativity. His equation had solutions corresponding to particles with negative energy, which he interpreted as antiparticles. One of the great mysteries of cosmology is why the universe contains so much more matter than antimatter. When the universe began, matter and antimatter should have been created in equal amounts. Yet today, antimatter is rare. Something broke the symmetry, allowing matter to dominate. This asymmetry is essential for our existence. Quantum entanglement does not allow faster than light communication. Entanglement is often misunderstood as allowing instant communication across vast distances. After all, Measuring one particle instantly affects its entangled partner. Could you not send a signal this way? The answer is no. When you measure an entangled particle, you get a random result. You cannot control what result you get. The person measuring the other particle also gets a random result. Only when you compare the results do you see the correlation. This comparison requires classical communication, which is limited by the speed of light. So, while the correlation is instantaneous, you cannot use it to send information faster than light. This preserves the principles of relativity, which forbid faster-than-light communication. Entanglement is a real, non-local connection, but it is subtle. It allows for phenomena like quantum cryptography, where the security of communication is guaranteed by the laws of quantum mechanics. But it does not enable instant messaging across the cosmos. Quantum mechanics has been experimentally verified countless times. Every prediction made by quantum mechanics that can be tested has been tested, often with extraordinary precision. The interference patterns in the double-slit experiment match theory perfectly. The energy levels of atoms are measured to incredible accuracy. The behavior of particles in accelerators, where they are smashed together at high energies, follows quantum predictions exactly. Quantum mechanics has been tested with photons, electrons, atoms, and even molecules made of hundreds of atoms. It has been tested at temperatures near absolute zero and at energies higher than those in the sun's core. It has been tested over distances from nanometers to kilometers. Every test has confirmed the theory. There are no known exceptions. This does not mean quantum mechanics is complete or final. There are unsolved questions, like how to reconcile it with gravity. But within its domain, quantum mechanics is as solid as any scientific theory can be. Schrödinger's cat is a thought experiment, not a real experiment. Erwin Schrödinger devised a famous thought experiment to illustrate the strangeness of quantum superposition. Imagine a cat in a sealed box with a vial of poison, a radioactive atom, and a detector. If the atom decays, the detector triggers the vial, killing the cat. If it does not decay, the cat lives. According to quantum mechanics, before you open the box, the atom is in a superposition of decayed and not decayed. This means the cat is in a superposition of dead and alive. Schrödinger intended this scenario to highlight what he saw as an absurdity in the standard interpretation of quantum mechanics. He did not believe a cat could be both alive and dead. The thought experiment raises deep questions about measurement, observation, and when quantum superpositions collapse into definite states. It is not meant to be taken literally. No one believes macroscopic objects like cats exist in such superpositions. Decoherence prevents it. But the thought experiment remains a powerful illustration of the puzzles at the heart of quantum mechanics. Quantum computers exploit superposition and entanglement to solve problems. Classical computers use bits that are either 0 or 1. Quantum computers use quantum bits or qubits, which can be in a superposition of 0 and 1 simultaneously. This allows a quantum computer to explore many possibilities at once. Entanglement allows qubits to be correlated in ways that classical bits cannot be, enabling even more powerful computations. Quantum computers are not faster at everything. They excel at specific problems, like factoring large numbers, searching databases, and simulating quantum systems. For many everyday tasks, classical computers are more efficient. But for certain problems, quantum computers could be exponentially faster. Building a practical quantum computer is extraordinarily difficult. Qubits are fragile. They decohere quickly, losing their quantum properties. Researchers are developing error correction techniques and better qubit designs. Progress is rapid, and small quantum computers already exist. In the coming decades, quantum computers may revolutionize fields like cryptography, materials science, and drug discovery. Quantum cryptography offers provably secure communication. Classical encryption relies on the difficulty of solving certain mathematical problems, like factoring large numbers. But with powerful enough computers, these codes can be broken. Quantum cryptography offers a different approach. It uses the principles of quantum mechanics to ensure security. One method, called quantum key distribution, involves sending photons in specific quantum states to establish a shared secret key. Any attempt to eavesdrop disturbs the quantum states, revealing the presence of an eavesdropper. The laws of physics, not just the limits of current technology, guarantee security. If someone tries to intercept the key, the disturbance is detected and the key is discarded. Quantum cryptography has been demonstrated over distances of hundreds of kilometers, both through fiber optic cables and through free space. Satellites have been used to establish quantum encrypted links between continents. This technology is not just theoretical. It is being deployed in real-world systems, offering a glimpse of a future where communication is fundamentally secure. Quantum mechanics challenges our understanding of reality. Before quantum mechanics, physics described a clockwork universe. Objects had definite positions and velocities. Causes preceded effects. The future was determined by the present. Quantum mechanics upended this picture. It introduced uncertainty, superposition, and non-locality. It suggested that reality is not fixed until observed. These ideas are difficult to accept. They challenge our intuition, which evolved to navigate a world of everyday objects, not subatomic particles. Philosophers and physicists have debated the meaning of quantum mechanics for nearly a century. Some interpretations, like the Copenhagen interpretation, say that particles do not have definite properties until measured. Others, like the many worlds interpretation, suggest that every measurement causes the universe to split into parallel branches, each containing a different outcome. Still others, like pilot wave theory, propose hidden variables that restore determinism. Despite these debates, the mathematical predictions of quantum mechanics are not in doubt. The theory works, regardless of how we interpret it. The universe at small scales is quantum mechanical, and we must learn to think in new ways to understand it. The many worlds interpretation suggests infinite parallel universes. One way to make sense of quantum mechanics is the many worlds interpretation proposed by Hugh Everett in 1957. It takes the Schrödinger equation completely seriously, without invoking wave function collapse. In this view, when a quantum measurement is made, the universe splits into multiple branches. In one branch, one outcome occurs. In another branch, a different outcome occurs. All possibilities are realized, just in different parallel worlds. From our perspective, we experience only one branch. We see a single outcome, but the other outcomes are just as real, happening in other branches we cannot access. This interpretation eliminates the need for a mysterious collapse. It preserves the deterministic evolution of the wave function, but it comes at a cost. an ever-branching multiverse of staggering complexity. Many physicists find the many worlds interpretation elegant. It requires no additional assumptions beyond the Schrödinger equation, but others find it extravagant, positing countless unobservable universes. The interpretation remains controversial, but it highlights how deeply quantum mechanics challenges our notions of reality. Quantum mechanics is not fully understood. Despite its success, quantum mechanics is not a complete or final theory. There are fundamental questions that remain unanswered. One is the measurement problem. The Schrödinger equation describes smooth, deterministic evolution, but measurements produce sudden, random outcomes. What exactly constitutes a measurement? When and why does the wave function collapse? Different interpretations offer different answers, but none are universally accepted. Another mystery is how to reconcile quantum mechanics with general relativity, Einstein's theory of gravity. Both theories are extraordinarily successful in their domains, but they are incompatible. Quantum mechanics describes the small. Relativity describes the large. Physicists seek a theory of quantum gravity that unifies them, but such a theory remains elusive. String theory and loop quantum gravity are promising approaches, but neither is proven. The quest to understand quantum mechanics fully continues. New experiments probe deeper into the quantum realm. New theories are proposed and tested. The strange, beautiful, and puzzling nature of quantum reality still holds secrets waiting to be uncovered. Quantum mechanics enables technologies we use every day. The impact of quantum mechanics extends far beyond laboratories and textbooks. It is woven into the fabric of modern life. Semiconductors, which rely on quantum properties of electrons, are in every electronic device. Lasers, which exploit stimulated emission, are used in everything from barcode scanners to fiber optic communication. MRI machines, which use the quantum behavior of atomic nuclei, allow doctors to see inside the human body without surgery. LEDs, which emit light through quantum processes, provide efficient lighting worldwide. Even GPS satellites rely on atomic clocks, which keep time using the quantum transitions of atoms. Without quantum mechanics, none of these technologies would exist. The theory that once seemed abstract and philosophical has become the foundation of the modern world. It is a testament to the power of understanding nature at its deepest level. Curiosity-driven research into the quantum realm has yielded practical benefits beyond anyone's imagination. Quantum teleportation transfers quantum states, not matter. Quantum teleportation sounds like science fiction, but it is a real phenomenon. It does not involve moving matter from one place to another. Instead, it transfers the quantum state of a particle. Here is how it works. Two particles are entangled and separated. One is with Alice, the other with Bob. Alice has a third particle whose state she wants to send to Bob. She performs a measurement on her two particles, the one to be teleported and her entangled particle. This measurement destroys the state of the original particle, but gives Alice information. She sends this information to Bob through a classical channel. Bob uses this information to manipulate his entangled particle, transforming it into the exact state of Alice's original particle. The state has been teleported. This process relies on entanglement and classical communication. It does not violate relativity because information still travels at light speed or slower. Quantum teleportation has been demonstrated with photons, atoms, and ions. It is a key technique for quantum communication networks and quantum computing. The quantum Zeno effect can freeze time for quantum systems. The quantum Zeno effect is a curious consequence of measurement in quantum mechanics. It is named after the ancient Greek philosopher Zeno, who proposed paradoxes about motion. The effect states that if you observe a quantum system continuously, you can prevent it from changing. Imagine a particle in a superposition that is gradually evolving toward a different state. If you measure it repeatedly, each measurement collapses the superposition back to its original state. With frequent enough measurements, the system never has time to evolve. It appears frozen. This effect has been observed in laboratories with atoms and particles. It shows how measurement actively shapes quantum systems. The quantum Zeno effect is not just a curiosity. It has practical applications in controlling quantum systems and improving quantum computing. By carefully timing measurements, researchers can stabilize qubits and extend their coherence times, making quantum computers more robust. Quantum field theory predicts the vacuum is not empty. In classical physics, empty space is truly empty, but in quantum field theory, the vacuum is teeming with activity. Virtual particles constantly pop in and out of existence, borrowing energy from the vacuum for brief moments allowed by the uncertainty principle. These particles are not directly observable, but their effects are. One consequence is the Casimir effect. When two metal plates are placed very close together in a vacuum, they experience an attractive force. This force arises because fewer virtual particles can fit between the plates than outside them, creating a pressure difference. The Casimir effect has been measured and matches quantum field theory predictions. Another consequence is the Lamb shift, a small change in the energy levels of hydrogen atoms caused by interactions with virtual photons. The vacuum, far from being empty, is a seething sea of quantum fluctuations. This has profound implications for cosmology and the nature of space itself. Quantum mechanics applies to atoms, molecules, and beyond. Quantum mechanics is not limited to individual particles. It describes atoms, which are systems of electrons orbiting a nucleus. It describes molecules, where atoms bond by sharing electrons in quantum mechanical orbitals. It even describes larger structures like quantum dots, tiny crystals just nanometers across that confine electrons in 3 dimensions, creating discrete energy levels like in atoms. Quantum mechanics has been observed in increasingly large systems. Experiments have shown interference patterns with molecules made of hundreds of atoms. Superconductors, where electrons form Cooper pairs and flow without resistance, exhibit quantum behavior on macroscopic scales. Superfluids, where liquid helium flows with zero viscosity, are another example. These phenomena show that quantum mechanics is not confined to the microscopic world. It is a fundamental theory that applies at all scales. The question is not whether quantum mechanics applies, but whether we can isolate systems well enough to observe its effects before decoherence takes over. The standard model of particle physics is a quantum theory. The most successful theory in all of physics is the standard model, which describes the fundamental particles and 3 of the 4 fundamental forces. It is a quantum field theory, built on the principles of quantum mechanics. The standard model includes quarks, which make up protons and neutrons. It includes leptons, like electrons, and neutrinos. It includes force-carrying particles, like photons for electromagnetism, W and Z bosons for the weak force, and gluons for the strong force. It includes the Higgs boson, which gives particles mass. The Standard Model has been tested in particle accelerators and experiments around the world. Its predictions are stunningly accurate. Yet it is not complete. It does not include gravity. It does not explain dark matter or dark energy. It does not explain why neutrinos have mass or why there is more matter than antimatter in the universe. Despite these gaps, the Standard Model is a monumental achievement, a testament to the power of quantum mechanics to describe the universe. Quantum mechanics shows that particles have no definite paths. In classical physics, a particle follows a definite trajectory. You can trace its path through space and time. But in quantum mechanics, particles do not have definite paths. Instead, they explore all possible paths simultaneously. This is the idea behind Richard Feynman's path integral formulation of quantum mechanics. To calculate the probability of a particle going from one point to another, you sum over all possible paths, even wildly improbable ones. Each path contributes to the total probability with a certain weight. Paths close to the classical trajectory contribute the most, which is why classical physics works for large objects. But at quantum scales, all paths matter. This approach is mathematically equivalent to the Schrödinger equation, but it offers a different perspective. It emphasizes that quantum particles do not have a single history. They have many overlapping histories, and the interference between these histories creates the patterns we observe. This view is central to modern quantum field theory and has deep connections to the nature of time and causality. Quantum mechanics is required to understand the periodic table. The periodic table of elements is a masterpiece of organization. Elements are arranged in rows and columns based on their chemical properties. But why do elements in the same column behave similarly? Quantum mechanics provides the answer. Electrons in atoms fill energy levels according to specific rules. Each level can hold a certain number of electrons. When a level is full, electrons fill the next level. The number of electrons in the outermost level determines an element's chemical behavior. Elements in the same column have the same number of outer electrons, which is why they react in similar ways. For example, all alkali metals have one electron in their outer level, making them highly reactive. All noble gases have full outer levels, making them inert. Without quantum mechanics, the periodic table would be a list of elements with no underlying logic. Quantum mechanics reveals the deep structure that makes chemistry possible. Quantum spin is an intrinsic property that has no classical equivalent. One of the most mysterious properties in quantum mechanics is spin. Every fundamental particle has spin, a kind of intrinsic angular momentum. But spin is not like a spinning ball or a rotating planet. It is purely quantum mechanical, with no analog in the classical world. Electrons, for example, have spin 1/2. This means that when you measure their spin along any axis, you get one of two results: spin up or spin down. There are no in-between values. You might think this means the electron is rotating, like a tiny sphere turning on its axis. But this picture fails. If electrons were truly spinning like classical objects, their surfaces would have to move faster than the speed of light to produce the observed angular momentum. Since this is impossible, spin must be something else. It is a fundamental property of the particle, like mass or charge, that arises from the deep mathematical structure of quantum mechanics. Spin was discovered experimentally in the 1920s, and it took the development of relativistic quantum theory by Paul Dirac to fully explain it. The Stern-Gerlach experiment revealed the quantization of spin. The first direct evidence for quantum spin came from the Stern-Gerlach experiment, performed in 1922. Otto Stern and Walther Gerlach sent a beam of silver atoms through an inhomogeneous magnetic field. Classical physics predicted that the atoms, acting like tiny magnets, should be deflected by varying amounts depending on their orientation. The result should be a continuous spread of positions on a detector screen. But that is not what happened. The beam split into two distinct spots. The atoms were deflected either up or down, with no intermediate positions. This showed that the magnetic moment of the atoms, which comes from the spin of their electrons, is quantized. It can only take on discrete values. The Stern-Gerlach experiment was one of the first demonstrations of quantum behavior in a tangible, observable way. It revealed that at the quantum level, nature is discrete, not continuous. The experiment continues to be a cornerstone of quantum mechanics education, illustrating the strangeness and precision of the quantum world. Spin determines whether particles are fermions or bosons. Particles in the universe fall into two broad categories based on their spin. Particles with half-integer spin, like 1/2 or 3/2, are called fermions. Particles with integer spin, like 0, 1, or 2, are called bosons. This distinction is not just a label. It has profound consequences for how particles behave. Fermions obey the Pauli exclusion principle. No two fermions can occupy the same quantum state at the same time. This is why electrons in an atom fill up different energy levels, and why matter has structure and stability. Bosons, on the other hand, love to occupy the same state. Any number of bosons can pile into the same quantum state, which is why lasers, where photons all share the same state, are possible. The connection between spin and statistics is given by the spin statistics theorem, a deep result in quantum field theory. It shows that in a universe governed by quantum mechanics and relativity, the spin of a particle determines its statistical behavior. This theorem is one of the most fundamental insights into the nature of reality. Quantum mechanics explains superconductivity. Superconductivity is the phenomenon where certain materials, when cooled below a critical temperature, conduct electricity with zero resistance. A current in a superconductor can flow forever without losing energy. This behavior is purely quantum mechanical. At low temperatures, electrons in a superconductor form pairs called Cooper pairs. These pairs act like bosons, even though individual electrons are fermions. The paired electrons condense into a single quantum state that extends throughout the material. In this state, the electrons move in perfect synchronization, flowing without scattering off impurities or vibrations in the lattice. Any resistance would require breaking a pair, which costs energy. If the temperature is low enough, there is not enough thermal energy to break pairs, so resistance vanishes. Superconductivity has practical applications, from MRI machines to particle accelerators. It also reveals the power of quantum mechanics to create macroscopic phenomena. A superconducting current is a quantum state that can be observed with the naked eye, flowing silently through a coil of wire, defying the everyday rules of physics. Superfluidity is another macroscopic quantum phenomenon. Superfluidity is similar to superconductivity, but occurs in fluids, most famously in liquid helium cooled to near absolute zero. A superfluid flows without any viscosity. It can climb up the walls of a container flow through tiny cracks, and even form thin films that defy gravity. Like superconductivity, superfluidity arises from quantum mechanics. The helium atoms, which are bosons, condense into a single quantum state called a Bose-Einstein condensate. In this state, all the atoms move together as one. There is no friction between them, because they are all described by the same wave function. Any disturbance would require exciting atoms out of the condensate, which costs energy. At low enough temperatures, the thermal energy is insufficient, and the fluid flows without resistance. Superfluidity is a window into the quantum world made visible. It shows that quantum mechanics is not confined to atoms and photons. Under the right conditions, it can govern the behavior of matter on scales we can see and touch. Quantum field theory unifies quantum mechanics and special relativity. Quantum mechanics, as originally formulated, does not include the effects of relativity. It works well for particles moving slowly compared to the speed of light. But to describe high-energy processes, like those in particle accelerators, we need a theory that combines quantum mechanics with Einstein's special relativity. That theory is quantum field theory. In this framework, particles are not fundamental objects. They are excitations of underlying fields that fill all of space. An electron is a ripple in the electron field. A photon is a ripple in the electromagnetic field. These fields are quantum mechanical, meaning their excitations follow the rules of superposition and entanglement. Quantum field theory is incredibly successful. It forms the basis of the Standard Model, which describes all known particles and forces except gravity. It predicts phenomena like particle creation and annihilation, where energy turns into matter and vice versa, in perfect agreement with experiments. Quantum field theory is the most complete description of the microscopic world we have. Virtual particles are a consequence of the uncertainty principle. In quantum field theory, the vacuum is not empty. It is filled with quantum fluctuations, brief appearances of particles and antiparticles that pop into existence and then annihilate each other. These are called virtual particles. They exist for such short times that they do not violate energy conservation, thanks to the uncertainty principle. The shorter their lifetime, the more energy they can borrow. Virtual particles are not just theoretical constructs. They have observable effects. The Casimir effect, where two metal plates in a vacuum attract each other, arises from virtual photons. The Lamb shift, a small change in the energy levels of hydrogen, is caused by virtual particles interacting with the electron. Even the magnetic moment of the electron receives small corrections from virtual particles. These effects have been measured with extraordinary precision, confirming that the quantum vacuum is a seething sea of activity. Virtual particles remind us that empty space is not truly empty. It is a dynamic, fluctuating entity shaped by the laws of quantum mechanics. Quantum chromodynamics describes the strong nuclear force. Inside protons and neutrons are particles called quarks, held together by the strong nuclear force. This force is described by quantum chromodynamics, a quantum field theory, where quarks interact by exchanging particles called gluons. The strong force has unusual properties. Unlike electromagnetism, which weakens with distance, the strong force becomes stronger as quarks are pulled apart. This is called confinement. Quarks are never found in isolation. They are always bound together in groups. When you try to separate two quarks, the energy you invest creates new quarks and antiquarks, which pair up with the originals. This is why we never see individual quarks in experiments, only composite particles like protons, neutrons, and mesons. Quantum chromodynamics also explains another phenomenon called asymptotic freedom. At very high energies, or very short distances, quarks interact weakly and behave almost like free particles. This behavior was unexpected and led to a Nobel Prize. Quantum chromodynamics is a cornerstone of the Standard Model and essential to understanding the structure of matter. The weak nuclear force is responsible for radioactive decay. The weak nuclear force is one of the four fundamental forces of nature. It is responsible for processes like beta decay, where a neutron turns into a proton, emitting an electron and a neutrino. This force is weak compared to electromagnetism and the strong force, but it plays a crucial role in the universe. The weak force is mediated by particles called W and Z bosons. These particles are massive, which is why the weak force has such a short range. It only acts over distances smaller than an atomic nucleus. The weak force is also unique in that it can change the type or flavor of quarks and leptons. It allows up quarks to turn into down quarks, and electrons to turn into neutrinos. Without the weak force, the sun would not shine. Nuclear fusion in the sun's core relies on weak interactions to convert protons into neutrons, allowing hydrogen to fuse into helium. The weak force is essential to the balance of matter in the universe and to the existence of complex structures like stars and galaxies. Neutrinos are ghostly particles that barely interact with matter. Neutrinos are among the most elusive particles in the universe. They have almost no mass and no electric charge. They interact only through the weak nuclear force, which means they pass through ordinary matter almost unhindered. Every second, trillions of neutrinos from the sun pass through your body without you noticing. Detecting neutrinos is extraordinarily difficult. It requires massive detectors, often buried deep underground to shield them from other particles. Neutrinos come in three types, or flavors, associated with electrons, muons, and tau particles. A remarkable discovery is that neutrinos can change flavors as they travel, a phenomenon called neutrino oscillation. This can only happen if neutrinos have mass, which was a surprise because the original Standard Model predicted they were massless. Neutrino oscillations have been confirmed by experiments and are now part of our understanding of particle physics. Neutrinos carry information from the cores of stars, from supernovae, and even from the Big Bang. They are messengers from the most extreme environments in the universe. Quantum mechanics allows for quantum computing. A classical computer uses bits that are either 0 or 1. A quantum computer uses quantum bits, or qubits, which can be in a superposition of 0 and 1. This allows a quantum computer to process many possibilities simultaneously. When qubits are entangled, the quantum computer can explore an exponentially large space of solutions. For certain problems, like factoring large numbers or simulating quantum systems, quantum computers can be vastly more efficient than classical computers. Building a quantum computer is challenging. Qubits are fragile and easily disrupted by their environment, a process called decoherence. Researchers are developing error correction techniques and better qubit designs to overcome this. Small quantum computers already exist and are solving specialized problems. In the future, Quantum computers may revolutionize fields like cryptography, drug discovery, and materials science. They represent a new frontier in technology, harnessing the strange rules of quantum mechanics to perform computations that were once thought impossible. Quantum algorithms can solve problems classical computers cannot. One of the most famous quantum algorithms is Shor's algorithm, which can factor large numbers exponentially faster than the best-known classical algorithms. This has huge implications for cryptography, since many encryption schemes rely on the difficulty of factoring. If large-scale quantum computers are built, they could break widely used encryption methods. Another important quantum algorithm is Grover's algorithm, which searches an unsorted database faster than any classical algorithm. Quantum computers can also simulate quantum systems directly, which is difficult for classical computers. This could accelerate the discovery of new materials, drugs, and chemical processes. Quantum algorithms do not make quantum computers faster at everything. For many tasks, classical computers are still better. But for specific problems, quantum algorithms offer a fundamental advantage. They exploit superposition and entanglement to explore solution spaces in ways that classical algorithms cannot. The development of quantum algorithms is an active area of research, with new discoveries happening regularly. Quantum error correction is essential for practical quantum computing. One of the biggest challenges in building quantum computers is decoherence. Qubits lose their quantum properties when they interact with their environment. This happens quickly, often within microseconds. Errors accumulate, and computations become unreliable. Quantum error correction addresses this problem by encoding a single logical qubit into multiple physical qubits. If some of the physical qubits decohere, the information in the logical qubit can still be recovered. This requires carefully designed codes and constant monitoring of the qubits. The overhead is significant. It may take hundreds or thousands of physical qubits to create a single, reliable, logical qubit. But progress is being made. Researchers are developing better error correction codes and improving the coherence times of qubits. Quantum error correction is not just an engineering challenge. It involves deep physics and mathematics, drawing on concepts from quantum mechanics, information theory, and coding theory. It is one of the keys to unlocking the full potential of quantum computing. Quantum annealing is a different approach to quantum computing. Most quantum computers use gate-based architectures, where qubits are manipulated with precise operations. Quantum annealing takes a different approach. It starts with a system in a simple quantum state and slowly evolves it toward the solution of an optimization problem. The system explores the energy landscape, using quantum tunneling to escape local minima and find the global minimum. Quantum annealing is well suited for optimization problems, like finding the best route for deliveries or the optimal configuration of a network. Quantum annealers already exist and are being used to solve real-world problems in logistics, finance, and machine learning. They are easier to build than gate-based quantum computers because they do not require the same level of control over individual qubits. However, they are not universal quantum computers. They can only solve certain types of problems. Quantum annealing shows that there are multiple paths to harnessing quantum mechanics for computation, each with its own strengths and applications. Quantum sensors exploit quantum effects for precise measurements. Quantum mechanics is not just about computing. It also enables incredibly sensitive sensors. Quantum sensors use phenomena like superposition and entanglement to measure physical quantities with unprecedented precision. Atomic clocks, which use the quantum transitions of atoms to keep time, are so accurate that they would lose less than a second over billions of years. Quantum magnetometers can detect magnetic fields millions of times weaker than the Earth's magnetic field. They are used in medicine to measure brain activity and in geology to map underground structures. Quantum gravimeters measure tiny variations in gravity, revealing hidden masses beneath the Earth's surface. These sensors are not just laboratory curiosities. They are becoming practical tools in navigation, communication, and scientific research. Quantum sensors show that the strange properties of quantum mechanics can be harnessed to probe the world with exquisite sensitivity, revealing details that were once invisible. Quantum communication networks are being developed. Quantum mechanics offers a new way to transmit information securely. Quantum key distribution allows two parties to share an encryption key that is provably secure. Any attempt to intercept the key disturbs the quantum states, revealing the eavesdropper. This security is guaranteed by the laws of physics, not just the limits of current technology. Quantum communication networks are being built to connect cities and even continents. Satellites have been used to establish quantum encrypted links over thousands of kilometers. These networks use photons traveling through fiber optic cables or through the atmosphere. The technology is still in its early stages, but it is rapidly maturing. In the future, quantum communication networks could provide a foundation for secure global communication, protecting sensitive data from cyber attacks. They represent a new paradigm in information security, one rooted in the fundamental principles of quantum mechanics. Quantum dots are nanoscale structures with unique properties. Quantum dots are tiny crystals of semiconductor material, just a few nanometers across. They are so small that quantum effects dominate their behavior. Electrons in a quantum dot are confined in all three dimensions, creating discrete energy levels like in an atom. This is why quantum dots are sometimes called artificial atoms. The energy levels, and thus the color of light they emit, depend on the size of the dot. Smaller dots emit blue light, larger dots emit red light. This tunability makes quantum dots useful in displays, where they can produce vibrant, pure colors. Quantum dots are also used in solar cells, medical imaging, and quantum computing. They are a beautiful example of how nanotechnology and quantum mechanics intersect. By engineering structures at the nanoscale, scientists can control quantum behavior and create materials with properties tailored for specific applications. Quantum dots show that the quantum world is not just something to study, it is something we can manipulate and engineer. Bose-Einstein condensates are a state of matter where quantum effects become macroscopic. When a gas of bosons is cooled to temperatures near absolute zero, something remarkable happens. The particles lose their individual identities and condense into a single quantum state. This is a Bose-Einstein condensate, predicted by Einstein and Indian physicist Satyendra Nath Bose in the 1920s. The first Bose-Einstein condensate was created in a laboratory in 1995. In a condensate, all the atoms occupy the same quantum state and move as one. They are described by a single wave function that extends throughout the sample. This makes quantum behavior visible on macroscopic scales. Waves in the condensate can be observed, and the condensate can be manipulated like a quantum object. Bose-Einstein condensates are used to study fundamental physics, test quantum theories, and develop new technologies like atom interferometers and quantum simulators. They are a testament to the power of quantum mechanics to produce states of matter that defy classical intuition. Quantum biology is an emerging field exploring quantum effects in living systems. For a long time, it was thought that quantum mechanics was irrelevant to biology. Living systems are warm, wet, and noisy, conditions that destroy quantum coherence. But evidence is mounting that quantum effects play a role in several biological processes. Photosynthesis, the process by which plants convert light into energy, appears to use quantum coherence to transfer energy efficiently. Birds may use quantum entanglement in their eyes to sense magnetic fields for navigation. Enzymes, which speed up chemical reactions in cells, may rely on quantum tunneling to work at the rates observed. Even the sense of smell may involve quantum effects, where molecules are recognized by their vibrational frequencies. Quantum biology is still a young field, and many questions remain, but it suggests that life has evolved to exploit quantum mechanics in ways we are only beginning to understand. The boundary between the quantum and classical worlds is not as sharp as once thought. Even in the messy, complex environment of a living cell, quantum effects can thrive. The Copenhagen interpretation says measurement collapses the wave function. The Copenhagen interpretation is one of the oldest and most influential ways of understanding quantum mechanics. It was developed by Niels Bohr and Werner Heisenberg in the 1920s. According to this interpretation, a quantum system exists in a superposition of states until it is measured. The act of measurement causes the wave function to collapse, leaving the system in a single definite state. What constitutes a measurement is somewhat vague. It is often described as an interaction with a macroscopic measuring device or an observation by a conscious observer. The Copenhagen interpretation does not attempt to explain what happens during collapse. It treats collapse as a fundamental process, something that just happens. This pragmatic approach has been successful. It allows physicists to make predictions and design experiments without worrying about the deeper meaning of the wave function. But it leaves many questions unanswered. Is collapse a real physical process, or just a change in our knowledge? Does it happen instantaneously? The Copenhagen interpretation has been debated for nearly a century and remains a topic of discussion in the foundations of quantum mechanics. The many worlds interpretation says all outcomes occur in parallel universes. The many worlds interpretation, proposed by Hugh Everett in 1957, offers a radically different view. It takes the wave function seriously and does not invoke collapse. Instead, it says that all possible outcomes of a quantum measurement actually occur. The universe splits into multiple branches, one for each outcome. In one branch, you measure spin up. In another branch, you measure spin down. Both branches are real, but they do not interact with each other. From your perspective, you experience only one outcome because you are in only one branch. But the other branches exist, containing other versions of you who experienced different outcomes. The many worlds interpretation is deterministic. The wave function evolves smoothly according to the Schrödinger equation. There is no collapse, no randomness. The apparent randomness comes from not knowing which branch you are in before the measurement. The many worlds interpretation is controversial. It requires accepting the existence of an enormous, perhaps infinite, number of parallel universes, but it has advantages. It is mathematically simple and avoids the measurement problem. It is taken seriously by many physicists working on the foundations of quantum mechanics. Pilot wave theory proposes particles have definite positions guided by a wave. Pilot wave theory, also called de Broglie-Bohm theory, is another interpretation of quantum mechanics. It was first proposed by Louis de Broglie and later developed by David Bohm. In this view, particles have definite positions at all times. They are not in a superposition, but they are guided by a wave, the pilot wave, which evolves according to the Schrödinger equation. The pilot wave influences the motion of the particle, causing it to follow trajectories that can seem strange and non-local. When you measure a particle, you are simply revealing its pre-existing position. There is no collapse. The wave continues to evolve, guiding the particle through space. Pilot wave theory reproduces all the predictions of standard quantum mechanics. It is a hidden variable theory, where the hidden variable is the particle's position. The theory is deterministic and provides a clear picture of what is happening at the microscopic level. However, it requires non-local influences. The pilot wave is affected instantly by distant measurements, which troubles some physicists. Pilot wave theory shows that quantum mechanics can be interpreted in very different ways, all consistent with the same experimental results. The measurement problem remains unresolved. The measurement problem is one of the deepest puzzles in quantum mechanics. It asks, how does a quantum system transition from a superposition of states to a single definite outcome when measured? The Schrödinger equation describes smooth, continuous evolution, but measurements seem to involve sudden, discontinuous changes. Different interpretations of quantum mechanics offer different answers. The Copenhagen interpretation says collapse just happens. The many worlds interpretation says all outcomes occur in parallel branches. Pilot wave theory says particles always have definite properties. But none of these answers is universally accepted. The measurement problem touches on fundamental questions about the nature of reality, the role of the observer, and the limits of scientific knowledge. It has philosophical and practical implications. Understanding the measurement problem could lead to new insights into quantum mechanics and perhaps to new technologies. After nearly a century of quantum mechanics, the measurement problem remains an active area of research and debate. Decoherence helps explain the transition from quantum to classical. One of the key insights into the measurement problem comes from the study of decoherence. Decoherence is the process by which a quantum system loses its coherence due to interactions with its environment. When a quantum system, like an electron in a superposition, interacts with air molecules, photons, or any external influence, it becomes entangled with the environment. Information about the superposition leaks out into the environment, and the system appears to collapse into a definite state. Decoherence happens very quickly for macroscopic objects. This is why we do not see everyday objects in superpositions. By the time we can observe them, they have already decohered. Decoherence provides a mechanism for the apparent collapse of the wave function. It explains why quantum systems behave classically in most situations. However, decoherence does not solve the measurement problem completely. It does not explain why we observe one outcome rather than another. the full superposition still exists in the combined system plus environment. Decoherence is a crucial piece of the puzzle, but it does not provide a complete answer. It is compatible with many interpretations of quantum mechanics. Quantum mechanics and gravity have not been unified. One of the greatest challenges in physics is to reconcile quantum mechanics with general relativity, Einstein's theory of gravity. Both theories are incredibly successful in their domains. Quantum mechanics describes the small. General relativity describes the large and the massive. But they are fundamentally incompatible. General relativity treats space and time as a smooth, continuous fabric. Quantum mechanics is built on discrete, probabilistic events. When you try to apply quantum mechanics to gravity, you run into problems. Calculations give infinite results that cannot be renormalized away, as they can in other quantum field theories. At very small scales, near the Planck length, quantum effects and gravitational effects become equally important. This is the realm of quantum gravity, and we do not have a consistent theory that describes it. String theory and loop quantum gravity are promising approaches, but neither is proven. Unifying quantum mechanics and gravity is one of the holy grails of theoretical physics. Solving it would transform our understanding of the universe, from the Big Bang to the interiors of black holes. String theory proposes that particles are tiny, vibrating strings. String theory is an attempt to unify all the forces of nature, including gravity, in a single framework. In string theory, the fundamental objects are not point particles, but tiny one-dimensional strings. These strings can vibrate in different patterns, and each pattern corresponds to a different particle. An electron is one vibration, a photon is another, and so on. String theory requires extra dimensions of space beyond the three we experience. These extra dimensions are compactified, curled up so small that we cannot detect them. String theory has some remarkable properties. It automatically includes gravity. It predicts the existence of particles like the graviton, which mediates the gravitational force. It offers a way to unify quantum mechanics and general relativity. However, string theory is not yet proven. It makes few testable predictions, and experiments to verify it are beyond current technology. String theory remains a vibrant area of research, with physicists exploring its mathematical structure and physical implications. Whether it describes our universe is still an open question. Loop quantum gravity offers an alternative approach to quantum gravity. Loop quantum gravity takes a different approach from string theory. It attempts to quantize space and time themselves. In this theory, space is not continuous, but made of tiny loops, forming a kind of quantum foam at the smallest scales. Time also becomes discrete, ticking forward in tiny steps. Loop quantum gravity does not require extra dimensions or supersymmetry. It works with the standard 4 dimensions of spacetime. The theory predicts that space has a minimum size, a quantum of volume, and that the Big Bang may have been preceded by a big bounce, a collapse of a previous universe. Loop quantum gravity has been successful in describing certain aspects of black holes and cosmology. But like string theory, it is not yet confirmed by experiment. The challenge for both theories is to make predictions that can be tested. Until then, they remain elegant mathematical frameworks, offering glimpses of how quantum mechanics and gravity might fit together. The quest to unify these two pillars of physics continues, with researchers exploring many possible paths. quantum mechanics reveals that reality is fundamentally probabilistic. Perhaps the deepest lesson of quantum mechanics is that reality, at its most fundamental level, is probabilistic. This is not just a limitation of our knowledge, it is a feature of nature itself. Particles do not have definite properties until measured. They exist in superpositions, clouds of possibility, until an observation forces them to choose. This randomness troubled many early physicists, including Einstein, who believed there must be a deeper, deterministic reality beneath the quantum surface. But decades of experiments have shown that quantum mechanics is correct. There are no hidden variables that determine outcomes in advance, at least not local ones. The universe is not a clockwork mechanism. It is a probabilistic tapestry, woven from chance and shaped by the laws of quantum mechanics. This realization is both unsettling and liberating. It means the future is not fixed. It means there is room for novelty, for the unexpected, for the genuinely new. Quantum mechanics has changed not just our understanding of physics, but our philosophical view of reality itself. Quantum mechanics shows us the universe is interconnected. Quantum entanglement reveals that the universe is deeply interconnected in ways that defy classical intuition. Particles that have interacted remain correlated, no matter how far apart they drift. Measuring one instantly affects the state of the other. This non-locality challenges our everyday notions of space and separation. It suggests that the universe is not made of isolated, independent parts. It is a web of relationships, a network of correlations that extends across space and time. This insight has profound implications. It hints that the whole is more fundamental than the parts. That the universe is not a collection of objects, but a unified, entangled system. Quantum mechanics teaches us humility. It shows that the world is stranger and more beautiful than we imagined. It invites us to see reality not as a machine, but as a dance, a flow of probabilities and connections. And it reminds us that we are part of this dance. Every atom in our bodies was once inside a star. Every quantum interaction we undergo is woven into the larger pattern of the cosmos. The mysteries of quantum mechanics continue to inspire. Nearly a century after its founding, quantum mechanics remains a source of wonder and inspiration. It has transformed our understanding of nature and given rise to technologies that shape the modern world. Yet it still holds mysteries. The measurement problem, the nature of the wave function, the meaning of probability, the relationship between quantum mechanics and gravity. These questions drive research in physics, philosophy, and mathematics. They challenge us to think more deeply about the nature of reality, and they remind us that science is not finished. There are always new puzzles to solve, new frontiers to explore. Quantum mechanics teaches us to embrace the strange, to question our assumptions, and to keep searching for deeper truths. It is a testament to human curiosity and creativity. And it is a bridge to the future, where quantum technologies and new discoveries will continue to reshape our world. Quantum mechanics is a gift to the imagination. Beyond its practical applications and theoretical insights, quantum mechanics is a gift to the imagination. It shows us that the universe is far richer than our everyday experience suggests. Particles can be waves. A single photon can be in two places at once. Entangled particles share a connection that transcends space. Virtual particles flicker in and out of existence in the vacuum. These ideas stretch the mind and open new ways of thinking. They remind us that reality is not confined to what we can see and touch. There are layers of complexity and beauty hidden beneath the surface. Quantum mechanics invites us to wonder, to explore, and to dream. It has inspired artists, writers, and thinkers across disciplines. And it continues to reveal new surprises, new patterns, new connections. In the end, quantum mechanics is not just a theory. It is a way of seeing the world, a lens through which the universe becomes more vivid, more intricate, and more mysterious. And that mystery is something to be savored, not solved. It is a reminder that we live in a cosmos that is endlessly fascinating. And now, as we reach the end of this journey through the quantum realm, let the weight of the day slip from your shoulders. You have traveled through ideas that challenge the very nature of reality, yet there is no need to hold on to them. Let them drift, like particles in a superposition, spreading gently into the background of your mind. Quantum mechanics has shown us that the universe is stranger and more beautiful than we could have imagined. It has revealed a world where particles dance between possibility and actuality, where distant objects remain forever connected, where the very act of observing shapes what is observed. These truths are profound, but they need not weigh on you now. The universe will continue its quantum dance while you rest. Electrons will keep spinning. Photons will keep traveling. Atoms will keep vibrating, all of it humming along in the background, following rules too subtle for the eye, but too precise to deny. You have done enough for today. You have peered into the heart of matter and glimpsed the invisible architecture of existence. Now, it is time to let go. Close your eyes and rest. Let your breathing slow and deepen. Let your thoughts dissolve like wave functions collapsing into stillness. The quantum world will be here tomorrow, waiting patiently, full of mysteries yet to be explored. But tonight, let yourself drift. Let the strangeness and beauty of the quantum realm carry you gently into sleep. Dream of particles and waves, of light and shadow, of connections that span the cosmos. Dream of a universe that is endlessly surprising, endlessly forgiving, endlessly yours to wonder at. Good night.